9 from tutorial 6. Here is our sequence, and as you can see, it is defined by means of a recursive formula. We have the first term, a1 equal to square root of 2, and every subsequent term is defined in terms of the previous term. So an plus 1 equals 2 square root of 2 plus an. In this question, we would like to show, without any assumptions whatsoever, that an is an increasing sequence, which is to say that for n, the present term an is less than or equal to the subsequent term an plus 1. And we also want to show that all the terms in our sequence are bounded from above by the value 2. How can we show this? Well, we will make use of a method of proof called mathematical induction. When we want to apply induction, there are two steps. The first is the base step, and the next is the induction step. So we will need to show that the base step is true, and then the induction step shows that all these subsequent steps are also going to be true for the statement that we want to prove. In this case, for part 1, we would like to have this statement to be shown true. Pn is that an plus 1 should be greater than or equal to an, which is what we have to show for the sequence to be increasing. So we take a look at the base step, where we will have to start from n equals to 1. Substituting it here would mean we need to show that a2 is greater than or equal to a1. So we need to prove this inequality. And just why is it true? It follows from this simple computation. This is the part of the statement that we want to prove. a2 is over here. We want to show it is greater than or equal to a1, which is square root of 2. But then all you have to do is just square both sides. This is if and only if 2 plus square root of 2 is greater than or equal to 2. But that is certainly true. If you add square root of 2 to 2, it's definitely greater than or equal to 2. So it is true, and that settles the base step for us. We have shown that when n equals to 1, the statement is true. P1 when n equals to 1 is true. Then we move on to our induction step. For the induction step, what we have to do first is to make an assumption. We assume that pk is true for some value of k. Then we need to prove that the next statement in our sequence must also be true. If we have pk, we want to show that pk plus 1 is also going to be true. Okay, so in our case, this is the statement for pk plus 1, and we want to prove it. How can we do so? We will just make use of the assumption that pk is true and the observation that our sequence is defined by means of a recursive formula. So here we will start with ak plus 1 greater than or equal to ak. That's the statement for pk. This is if and only if, well, we have this inequality where we just add 2 to both sides. It's still true. This is, or rather, it is equivalent to the starting statement. This is also equivalent to what we would have here by taking the square root of both sides. So we have here a chain of equivalent conditions. If you start with pk, this is equivalent to the next statement, the next inequality, and it is equivalent to the final inequality over here. And what is this? This is just by means of our recursive formula, ak plus 2 greater than or equal to ak plus 1. We recognize square root of 2 plus ak plus 1 from our formula is just ak plus 2, and similarly this is ak plus 1. But the statement here is the same thing as pk plus 1. That's right here. In other words, we have shown that once we assume that ak plus 1 greater than or equal to ak is true, we can use a series of computations and show that it would imply that pk plus 1 is also true. And therefore, by using mathematical induction, once you know that the base step has been proved and the induction step has also been proved, mathematical induction shows you that you have proved that Pn is true for all values of n, for all n as you see here. Therefore, we have shown that the sequence in question, An, is an increasing sequence. So that settles the first part. For the second part, once again we will make use of mathematical induction. What is the statement that we're trying to prove? It is that An is less than or equal to 2 for all values of n. So the statement that we have to look at is Pn, which is An less than or equal to 2. We begin with the base step, so we will set n equal to 1. In this case, we will look at a1, which is given by the value square root of 2, and certainly it is true that it is less than or equal to 2. That is clear for us. So the base step is true. We then move on to the induction step, where we have to assume that pk is true. If pk is true, we want to prove that the next statement, pk plus 1, is also going to be true. And we can use pk once again. So pk tells us that ak is less than or equal to 2 by assumption. This is equivalent to, well, adding 2 to both sides, which would give us 2 plus ak less than or equal to 4. And this inequality is equivalent to what we would get by taking the square root of both sides. So taking the square root here gives us ak plus 1 by means of our recursive formula. So ak plus 1 is this square root of 2 plus ak, and it's less than or equal to square root of 4, which is just 2. Which is just saying that ak plus 1 is less than or equals to 2, and that is the statement pk plus 1. So we have completed the proof of the induction step, that if we assume that pk is true, we know that pk plus 1 is also going to be true. Therefore, applying mathematical induction once again, we see that we have shown that the sequence is bounded from above by the value 2 for all values of n. And as a remark, we note that if you have a sequence that is defined by a recursive formula, so a sequence of this nature where you have the starting term and every term after that is defined in terms of the previous term, then you can use mathematical induction to study the sequence quite effectively. So mathematical induction is a useful method to prove various properties of our sequence. So from the two parts that we have shown, the first is that the sequence An is increasing, and the next is that it is bounded from above by a certain value 2. Therefore, we can apply a result to show that the sequence is convergent, and that's the monotonic sequence theorem. If you know that your sequence is monotonically increasing and bounded from above, it tells you that the sequence must converge, and it converges therefore to a certain value L, and you can compute the value as we did in the tutorial. So this is all that we will do for question 9.